All right, welcome everybody. Our first speaker for today is Adele Jackson from the University of Oxford, who's going to tell us about triangulation complexity of a hyperbolic mapping tori. All right, Adele.
Awesome. Well, I just want to say thanks to the organizers for putting this conference together. It's really great to be able to be here. But also it's 11 p.m. where I am, so please ask your questions early because I'm only going to get less coherent as this goes on. But all right, so I guess I mostly wanted to provide a bit of an introduction to triangulation complexity and why you might think it's interesting, and then hopefully we'll be able to get to some mapping tori at the end. Okay, great. So I like three manifolds, and in particular, I like three manifold invariants. And so the triangulation complexity of a three manifold, where for me, all my three manifolds are going to be compact and orientable, is the minimal number of tetrahedra in any triangulation of my manifold. Where, I mean, this is just a technical note, but my triangulation might be ideal. It's not necessarily simplicial, which we'll see some examples of. Okay, so speaking of some examples, so we can take a torus, which isn't a three manifold, but we can do the same definition with triangles instead. And so what's that going to be? Well, my favorite triangulation of a torus is this one. And we can see that, in fact, this is because the smallest number of triangles we can manage. We certainly can't do zero triangles because we can't build any surfaces with no triangles. And if you think about it a little bit, you can see that you've got to have an even number of triangles, basically because the number of edges around a triangle is odd and they've all got to pair up. Okay, so that tells you that the smallest you can possibly do is going to be 2. Okay, but I promised you three manifolds. Let's look at another small one. So the 3-sphere. Well, similarly with torus, it turns out we can do this in like the smallest possible number of tetrahedra. So that's going to be 1. And so all I need to do for you is give you an example of this. So what's that going to be? Well, we're going to take a tetrahedron, and then we're going to take 2 of the faces, and we're just going to fold them over their common edge. And so when you do that, what you're going to get is you're going to get a ball with the spherical boundary just with 2 triangles, the sort of northern and southern hemispheres. And then we can do this again. We can just identify them again. And so when we glue that up, it might be easier to see if you sort of cut along the equator, and you can see that we're actually just taking 2 balls, sort of the top and bottom halves of this, and we're identifying their boundaries. And we know that that's the 3-sphere. Okay, so that's 1. And then, well, it turns out that if you think about what are all the possible things you can do with one tetrahedron, you get 2 more lens spaces, and that's it. So a couple more numbers that we get is for the sphere time, like S2 times S1, we're going to get 2 because we can just exhaustively check that we can't do it with 1 and we can do it with 2. And similarly, nothing particularly insightful, the 3 torus, we get 6. I should note that these bottom 2, when you're doing these exhaustive checks, obviously you don't really want to do that by hand. So there are some computer programs like Regina that are fantastic for this sort of thing. Anyway, so that's some examples, but why might you care? One reason we might care is that triangulation complexity is really nice in that it lets us enumerate all the 3 manifolds. So this is sort of in the same way that if you like knots, right, we often list them by crossing number. There are lots of tables of that sort of thing. And that's because if you've got a given crossing number, there are only finitely many things that you can do to connect them. And so you know that there's only like finitely many knots for any given crossing number. Similarly, in this case, finitely many tetrahedra means finitely many 3 manifolds, right? So just to put that down, because that's something that makes this different to like listing the Hagar genus or something like that, where you get like infinitely many for each number. And it's not, from my point of view, it's not as nice. But another reason that they come up particularly maybe in the last 30 years is that they're fantastic for computations. So if you like, I mean, if you like these things, I probably don't have to sell you on triangulations, but normal surface theory is like an enormously powerful tool that's been used in proofs the last half century or so. So that's used. So that was used to prove, say, unknot recognition, is NP complete, that sort of thing. Like give algorithms for this sort of thing, and also more maybe concretely, Snappy and Regina are some computer programs that you might be familiar with if you like three manifolds, and they're things that you really can just chuck a triangulation in and be like, what is this? Tell me about it. What's hyperbolic volume? You know, lots of those sorts of questions. So that's nice. But I guess one question that jumps out at me here is that triangulation complexity, like cutting things into tetrahedra, is really combinatorial. And these tetrahedra, like from the point of view of maybe the geometric or the topological structure of the free manifold, might not seem very natural. So we might want to understand like how this invariant relates to things that we understand better, things that are maybe a bit more topological. And so I thought I might give two examples of these connections. One maybe where the connection is sort of what we expect, and one where it might be a little bit more surprising. Okay, so first of all, let's talk about knot complements. Yep, so what's going on here? So I was saying before that we often list knots off by crossing number because it has this similar property where there's like finitely many knots for the certain crossing number, right? And it's a pretty natural question to ask how this relates to the triangulation complexity of the complement. And maybe, so in this, so we've got like the crossing number of our knot related to the knot complement. And why maybe the knot complement might be a natural thing to think about is that if we've got a knot embedded in the three sphere, then it's determined entirely by its complement. So you can maybe sort of think of them as the same, as like they're sort of the same amount of information. Okay, so one thing that you see a lot with triangulation complexity is that getting upper bounds is a lot easier than lower bounds. So you might have seen that in the couple of examples that I did concretely, it really was like, here's an upper bound and then we checked it, or here's an upper bound and we can't do any better. Because all you've got to do is actually just give a triangulation. And this is definitely one case where that's true. So first of all, the upper bound. So it turns out that the triangulation complexity of the knot complement is at most 4 times the crossing number of the knot. And I think this is due to, I think there's some stuff in Snappy about it. And Dylan Thurston. And I don't, unfortunately, have time to give the picture here, but like you really can just like draw the picture of what are the 4 tetrahedra you put around each crossing and how do they glue up. You know, it's really hands-on. In the other direction, we get something that, well, I mean, we do get a bound, which is exciting, but it's maybe a little harder to understand. We get this thing, which I should note isn't, as far as I know, actually on the archive. I heard about this in a talk like last month. So this is your hot off the press triangulation complexity results. So you should email these people if you want to hear more. And that took and I think that took like quite a lot of work and really understanding these triangulations and normal surfaces. So, but to me, this result, like fundamentally, right, is saying that if we've got really high triangulation complexity, then we have to have had a really high crossing number. And if we've got really high crossing number, then okay, maybe, I mean, with this horrific exponential, like maybe our triangulation complexity wasn't high, but it's at least got to grow, right? This seems like fairly natural. So here's a different example. So where maybe we don't get this growth, this connection. Okay. So hyperbolic volume. Okay. So hyperbolic three manifolds are really interesting. And so let's suppose, and so we can get some results here. So let's suppose that our manifold is closed and hyperbolic, and so that's equivalent to M being the quotient of hyperbolic three space by some discrete subgroup of the isometry group. Turns out. And if you've got like a given hyperbolic structure on this, right, you can calculate the hyperbolic volume. And then by Mostel rigidity, we know that that we don't have multiple hyperbolic structures on the same manifold. So the hyperbolic volume of M is a topological invariant. So that's like a well-defined thing. And by some work of Gromov and Thurston, we can relate so this hyperbolic volume is really sort of measuring how big our three manifold is, right? And we've got our triangulation complexity that also maybe measures how big our three manifold is. And so we do get an inequality, which is really nice. So by Gromov and Thurston, and they tell us that if you look at the volume and then you look at what are the biggest possible geometric tetrahedra in hyperbolic three space, those are going to be our regular tetrahedra that go all the way up to the boundary, right? And they tell us that you sort of can't do any better than that, right? That if you've got really big volume, those are the biggest tetrahedra you can use in terms of using up volume, sort of. Okay, so that's really cool. But a natural question to ask, to my mind, is does this mean that that all this time I've been telling you about triangulation complexity, and I've just been secretly telling you about hyperbolic volume? And I mean, that'd be really cool if it was true. But it turns out you can see that it's not true. So hyperbolic Dane surgery tells us is a way where given a finite volume hyperbolic manifold, where this one isn't closed, it has toroidal boundary, then what we can do is we can glue in a solid torus, right? And this is going to give us, by all those gluing maps, an infinite family of three manifolds. And so for our purposes, what we get is we get an infinite family of three manifolds with almost all of them also a hyperbolic, such that they've got bounded volume by the volume of the manifold that we started with. Okay, so it might not be immediately obvious how this is relevant to us, but you might remember that what's really nice about this combinatorial definition is that there's only finitely many three manifolds for each triangulation complexity, right? And so if we were to get any sort of relationship of the form triangulation complexity of M is at most some function of the volume, then that would tell us that this infinite family of three manifolds all had triangulation complexity bounded above by some number. And that's impossible. One of these is finite, one of these is infinite. So we can't ever have that. Yep. Okay, so we are measuring something different, which is nice. All right, so I might get on to talking about some mapping tori, if there are any questions.
I have a question.
Yeah.
Could you go back to the previous slide, please?
Yeah, easy.
So this was, the Gromov-Thurston result gives you a lower bound to triangulation complexity. Okay, sorry.
Yeah.
I missed that.
No, thanks. No, thanks for asking. Yeah. So it tells us that like if we've got high hyperbolic volume, we have to have like we can't have super low triangulation complexity.
And then just now you just argued that delta m
You
cannot
can't.
be bounded above by volume. Okay.
Yeah, that can't happen
Okay.
for any
Cool.
function.
Thanks.
That's just impossible. Okay. No, thanks for clarifying. Any other questions? Nope. Okay. Well then, let's chat about mapping tori, shall we? Okay. So, what is a mapping torus? If I've got a closed surface and I've got a mapping class, so a homeomorphism from that surface to itself, then my mapping torus is what happens when I take my surface, I thicken it up, and I glue that together. So I like to draw this picture. Right, so we just thicken up and then we glue up by our map phi. These are this is a really nice family of 3 manifolds. It's one thing that's pretty cool here is that you can have like mapping classes going from all different genuses of surface that all give you the same topological 3 manifold. Right, so I could have like a mapping class for my 2 genus, a mapping class for my 5 genus, mapping class for my 500 genus, where all of my mapping tori are the same manifold. Okay, and a question that I'd be actually really interested to, if anyone's got any insight into this, I'd be really interested to hear about it, is like how are these all connected? Right, like I've got all these mapping classes on all these different surfaces, and so what on earth is going on there? So like it's this sort of question, right? Like how's the geometry of my manifold related to the dynamics of my map? Because this tells me, if I can find some relationship, this tells me something in common about all my different maps, which like there are going to be infinitely many in general. Yeah, and this was a question that was posed by Fuda and Schleimer, and I really would be very interested to hear about any thoughts anyone's got. Triangulation complexity gives us one answer to that, but I might just talk about a couple of different results in this direction first. Let's suppose that we're in the hyperbolic case, as we were discussing before, and that's equivalent to our map being pseudo-Nosov by the work of Thurston. Okay, so there's one particular sort of measure of the dynamics of our map phi that's going to be particularly important for us, and that's stable translation length. So what is this saying? Well, let's think about what this is going to mean, say, for 2 maps. So say that we've got one map that's just acting by a translation, which just takes this point to this point to this point, and then say we've got another map that's finite order, that takes us round in some circle. Okay, so what's this going to do? Well, for our first map here, if we plug in this point x here, then we find that as we like apply phi1 over and over and over again, we just keep moving by this constant factor. Okay, so like if this distance here was if this distance here was, say, L, then we find that this is going to give us just that L back. Okay, but then phi2, in contrast, what we see is that the first time we go around, we move, but then the second time we come back again. So we're going to get, like in this set that we're taking the infimum of, we're going to get all of these zeros from every time we just come back and back and back. And so this is going to give us 0. So this is sort of measuring how much our map moves us, and something something that you can check is that this is actually independent of the this is actually independent of the point x that we chose. Okay, so So we've got this map acting on a metric space, and then we're sort of measuring how far it takes things. Okay, so what are we going to get out of that? Well, one result that Brock proved is that, oh yeah, sorry, and I'll just abbreviate stable translation length as STL because that's way too long to write out. So one result that Brock proved is that in the case where our mapping torus is hyperbolic, so when our map was pseudo-Anosov, then the hyperbolic volume of our map is approximately like bounded by some constants on each side, like think like a quasi-isometry sort of thing. The stable translation length of our map acting on the pants graph. Okay. So here this is very much doing this like geometry of manifold dynamics of our map. Okay, so that's something, and then I guess this pants graph and this action, if you like, that's all very combinatorial. If maybe you like something a little bit more geometric, that's all quasi-isometric to phi acting on the Teichmüller space of our surface with the Weil-Petersen metric. Sorry, Weil-Petersen. Sorry, I don't know how to say things. Okay, sorry about the space. But okay, so then another result sort of in that direction is when Friedrichsheimer asked this question about the geometry of the dynamics. In that paper, they proved the following result. So when our surface that our phi was acting on has boundary, we get the volume of the cusps in our mapping torus grows like, in that similar way, the stable translation length of phi in the arc complex. Okay, cool. So this has all been about like volume, and so the result in terms of triangulation complexity that I've got for you is the following. So this is from Lackenby by herself in 2019, which tells us that the triangulation complexity of our manifold, again assuming it's hyperbolic, is like the stable translation length of phi in the triangulation graph. And so what that triangulation graph is it's going to be the graph where the vertices are one vertex triangulations of our surface, and then the edges are these two partner moves. So you take two adjacent triangles and you flip the diagonal. And just in, yeah, and so sort of, just in my last minute, sort of what the connection here is that you can like make these partner moves happen. I mean, sorry, what the upper bound is, which is always going to be easier, is that you can make these partner moves happen by sort of gluing on tori. So if I want to go from like the one on the left to the one on the right, then I can sort of glue on this torus, if you can sort of see that. Sorry, not torus, tetrahedron, sorry. You can glue on this tetrahedron, and so you sort of end up gluing on one tetrahedron for each edge in your path. All right, well, yeah, well, thank you very much for your attention.
Thank you, Adele. I would like to ask people to unmute and give a round of applause to our speaker. And now, if anyone has a question, then you're welcome to ask.
I have a question, actually. Firstly, thanks for your talk. It was really, really nice. Could you go back maybe 5 slides or so to the point where you were talking about the mapping tori, and you were saying something about, oh, I think next one, yes. You were saying you can get the same 3 manifold from like different genus surfaces by using different mapping classes. Do you have like a cool example where you can see that directly? It doesn't have to be
that's
cool, just an example.
No, that's a really good question. I think off the top of my head, no, without worrying, I'm going to say something wrong. But maybe something that's something that's neat here. That I mean, this is some fairly like sort of deep stuff. But I don't know if people here are familiar with like the Thurston norm ball. So it's sort of this idea that you can put a norm on the second homology. So it's a Thurston norm like on H2 of your 3 manifold. And it turns out that when you look at like the norm, at like the unit 1 ball of this, you get this polytope. And our lattice points in that are going to correspond. Like this is like takes some work, but like one thing that's really, really cool is that if you've got a face of that and like lattice points in that, sorry, the points in that, a lot of them are going to correspond to actual like second homology elements. They're going to be on rays. Then if one of those corresponds to one of these surfaces that's like a fiber that cuts it into surface cross interval, then everything in that face is going to correspond to a fiber. So you just like have like this big family, just like boom, which is really cool. That doesn't really give you an explicit example, but it tells you there are lots of them.
Yeah, thank you.
Yeah.
I have a question or maybe a comment. So the hyperbolic volume is also related to the simplicial volume of the 3 manifold, right? And they're like equal or something up to a factor.
Yeah, they're actually that what you were asking about this
Yes.
here. They're equal up to exactly that factor. Like what's going on here is that the what's going on in this inequality.
Is that the proof of this fact?
Yeah, that's exactly the proof. Yeah,
Oh,
I just didn't want to mention simplicial volume. So like really, it's just this is at least simplicial volume.
Okay.
Which equals this thing. Yeah.
Also, the stable translation length. Is there like so I'm not so familiar with tacular theory. Is there an actual translation length for pseudo-Anosovs acting on the tacular space in any metric? As in like the infimum of the distances between any point and its image. Is that the same as a stable translation length, or is it different? Does it even exist?
Yeah, I mean, I feel like Tagmuller stuff isn't. I feel like I'm worried that there's probably people here who know more about this stuff than I do. But yeah, like pseudo-Anosov should take you translate you along this big axis, right? And if you've got that sort of axis behavior, then like I think you're talking about like what we call like translation length, where you just look at the infimum, as you're saying. And I think in that case they'll be equal, but in general they're like within some constants, but they're not necessarily equal.
You mean in general for other mapping classes?
Actually, sorry. The statement that I'm really confident in is that they're definitely within some constants.
Okay.
Yeah, I'm not sure if they're equal. I think like Purcell and Lackenby in their paper deal with exactly this question, but I'm not sure what the answer is.
Okay, thanks.
Yeah, thanks.
So about your theorem at the very end, yeah, the last slide. So
yeah.
Is that actually useful for computations or anything of the sort? Because it seems like, I mean, to understand this triangulation graph, you already have to understand all the triangulations.
Yeah, no, good question. Yeah, actually, it is something that you can compute. I'm not sure if you're familiar with like train tracks and that sort of thing. Yeah, okay, cool. So what do I want to say? As it turns out, I mean, this is very ham-wavy, but you get associated to a pseudo-Anosov. So let me just let me just jump to it. Something. Okay, great. So associated to a pseudo-Nosov, you like a pseudo-Nosov, you can build like some particularly nice trivalent graphs, which like because like so the pseudo-Nosov is fixing this like is fixing a foliation on your surface in particular. And you can sort of compress that you can sort of just compress that. Let's squint at it and be like, what graph should this be? And this gives you this thing called a train track. And then if it turns out that if you start doing this is stuff at Eagle, in Eagle. So it turns out that if you start doing these things called maximal splits on this, then you get this family, right? Tau 1, Tau 2 of train tracks. And it turns out that eventually it becomes periodic. Like you get Tau n, and then you get like Tau n plus k, and this is equal to phi of Tau n. And whatever like this k number was, is a quasi-geodesic, like this ends up being a quasi-geodesic in your triangulation graph. So this thing gives you the stable translation length because it gives you like this axis the pseudo-Nosov is going along. Sorry, I feel like this is very hand-wavy, but basically like, yes, in practice, if you're given a pseudo-Nosov, you actually like can sit down and build this combinatorial object if you feel like it, and then compute some stuff. And I think Bespina and Handel made this like specific, and I think it's been implemented, but don't quote me on that.
Okay, thanks.
Is that your question?
Sure, yeah, thanks.
I have a question. It seems to me that you have some slides that you not presented for us. Can you show it for us at least a little quickly?
Sure. I mean, this is just called a run over time, as you know, as one does. But I guess I was just going to maybe talk a little bit about, talk about the upper bound in more than about a sentence, which is really just a picture. And maybe talk about how this behaves when you compose your map with a Dane twist, where it just turns out it does what you think it should do. You get this result. So, this is for an Nosov map. If you compose with a power of a Dane twist, then like you can draw a really naive picture where you just add on a linear amount of tetrahedra for every, you add on a constant amount for every time you apply the Dane twist, and that's up to some constants the best you can do. So, yeah. But yeah.
All right, so let's thank Adele once more.
Thanks for your time.
Great talk.